Okay, welcome now to week 4 of 6. This is a paper 1 booklet, so a non-calculator booklet again. So don't use your calculators in anything here unless I tell you any different on here. The topics are there. I won't run through them. But you can see the ones in bold are higher, so towards the back of the book. The ones not in bold are the first half. Although there's some nasty stuff, I've got to say, even in the non-bold stuff here. So let's start with our first topic. Again, you can see that about 18 to 25 out of your 70 marks are in this booklet here. Okay. Got a formula list in this one for you as well, so just to get used to it. Having said that, none of the topics here, I don't think are going to use any of these formulas, but just to familiarize yourself with it. So what a Venn diagram looks like, okay, is this. Yeah, you can see here. Okay. What I want to pick. Hello there. Welcome to week 4 of 6. This is a paper 1 booklet that's non-calculator. These are the topics in here. Anything non-bold, again, is intermediate. So first half of the paper, anything bold is second half of the paper and is your higher, your A and A star topics. About 18 to 25 marks out of the 70 in here. So about a third of the paper is in here. I've started putting the formula list into all booklets. However, there are no topics in here that will rely on any of the formulas from the formula list. So we're going to start with topic 1, which is Venn diagrams. And I'm actually going to take us away from here into probably the more difficult example, which is this one. Okay, I'm going to have to zoom in a little bit. Hopefully you can still read it because I know the quality of the screen isn't great. So if we go there, hopefully you can see that. Now, what we're told here is about a group of students taking part in the Eisteddfod. Okay. First of all, I want to draw your attention to what a Venn diagram looks like. A Venn diagram is 2 or 3, in this case, overlapping circles, okay, with a box around them, and this symbol, which is like an E symbol, which means the universal set, okay? Basically, who am I putting in to the Venn diagram is the universal set. So if this is a class of children or a group of pupils, the universal set is the group of pupils. Don't worry about that. You'll just put that, if ever you draw a Venn diagram, you'll put that sort of E symbol on the outside of your box with your overlapping groups inside and labels for each circle as well. So the big word in a question like this is only. And I'll explain what that I mean now, okay? Only. If I only sing, I belong in this because I don't do drama, so I would be here, okay? If I only sing. If I only dance, I would be here, right? However, if I sing, I could be anywhere within the circle because that doesn't mean I don't dance or I don't act or whatever the bottom one is. We'll see that in a second. But only means you can put the number straight on. If you don't see only, you can't put the number straight on. That'll make more sense when we do an example now. The other thing I want to say is, in this type of Venn diagram, the numbers that we're putting in are the amount of people. So how many dance, how many sing, how many do both, how many do neither, that kind of thing, okay? What you'll see in a second is an example where we are putting individual numbers onto a Venn diagram in the right place rather than this being a number of people. Okay, so let's read. Two of them only took part in dancing, which is why that 2 is there. 5 only took part in reciting. Let me scroll down a bit. Okay, so here's reciting at the bottom. So 5 only did reciting. So I'm able to put that 5 on. No one took part in both a reciting and a dancing competition. So there was nobody who did recital and dance, which is this bit here. 3 took part in both a singing and a dancing competition, which is this overlap here, singing and dancing overlap. 9 took part in reciting. And you might look on going, no, but I've got 5 if I'm reciting. But those 5 did only reciting. This doesn't say only. These 9 did reciting, but could have done other things as well. So include this 5, include this 0, and include this 0. So there's only this kind of gap where the other people who did reciting could go. So 9 take away 5 means that there's 4 in there. So 9 altogether. And the same here. 22 took part in singing. Well, we've already got 7 singers, 4 and 3. So take that 7 away from 22 means that there is 15 in here. Let's read the rest of the question. The Venn diagram below shows some of the above information. The universal set E contains all of the pupils in the group. Basically, I'm going to put all the pupils onto the Venn diagram somewhere. Okay. One of the pupils in the group is chosen at random. What is the probability that this person only, there's that word, so not took part in singing, only took part in singing, sorry. So that is those 15, okay? But the probability of choosing that person at random is 15 out of, add these all together, 15, 18, 20, 24, 29. And unless it asks you to simplify your answer, you can leave it like that. In this case, it couldn't be simplified anyway. Now, another type of question, I'll go back to something like this, okay, involves you drawing the Venn diagram. The universal set E, so these are the numbers we're going to put on, is all of the numbers from 74 to 80. So individually, we have to put these numbers in the right place. Set A is the first circle. This isn't going to be the best drawing. Set B is the second circle. You can do a better job than this. Right? Remember to put a rectangle around and an E there. So that's the setup of a Venn diagram. Set A is even numbers, so I'm going to write even there. And set B is multiples of 3. So I'll put multiples of, or just mult of 3 there. Okay. And the numbers that I'm putting on are everything from 74 to 80, including 74 and 80. So 74 is even. Is 74 in the 3 times table? You'd have to take your time and work it out, but it is not. So 74 is in there. 75 is not even, but it is in the 3 times table. 76 is even. 77 is not even, but it's not in the 3 times table, so it would go outside of the circles. 78 is even and in the 3 times table, so it goes in the middle. 79 is not even and not a multiple of 3, so it goes outside. And 80 is even, but not in the 3 times table, so it goes over here. Okay. Again, I could follow that up then with, these are individual numbers. What is the probability of picking a multiple of 3? Well, it would be both those numbers. So there are 2 numbers there out of 1, 2, 3, 4, 5, 6, 7. So a slightly different way of doing things because we're looking at individual numbers rather than a number of people, right? You can try the rest of those. That's the end of Venn diagrams. Our videos, straight line graphs and parallel and perpendicular lines. Oh, it could be bitty, this. Could be a lot of like little 1 mark questions and stuff with varying different things going on in them. So we'll cover as much as we can, go through a few different questions and just being asked to do. Okay, so first of all, the equation of a straight line is y equals mx plus c. The number that goes before the x, m, okay, is the gradient of the graph. All right, I've given myself some extra room to put some notes here. And that number at the end, C, is the y-intercept, where the graph cuts the y-axis, okay? So let's talk a little bit about gradient first, okay? Let's look at this. Now, what I'm going to do here, I'm going to give you 2 points. -5 there, and I'm going to give you this point on the x-axis as, let's make this not too bad, let's call it 15. I don't know, it'll do. I know that scale is way out, but go with it, okay? So first of all, the y-intercept, the actual number 15 is irrelevant to me here, okay, for my equation, right? But the y-intercept, where this cuts the y-axis, is -5. So the equation of this line at the moment is y equals mx, but the c bit, the y-intercept, is -5, so I can put that in. Now, how do I work out the gradient? To work out the gradient, I need 2 nice points on the line. Well, I've deliberately given you 2 nice points. I've got this one and this one. Once you've got 2 nice points, okay, you go along and up to that point there, right? For going from there to there, we have gone along the x-axis 15, And going up from there to there, we've gone from -5 up to 0, so we've gone up 5. M, the gradient, is the change in y divided by, you might not be able to see that, but hopefully you can, the change in x. So in this case, up over across, right? So I've gone up 5 in the time I've gone across 15. It's important we go that way around, not the other way, okay? Which is 1 over 3, simplified, or a third. Don't change it to a decimal in this case. So my gradient is a third, right? So the equation on my line is y equals a third x, where my gradient goes, -5 for that line, okay? Now, let's not, that was an example where I drew the line and I asked you to find the gradient and the y-intercept and write the kind of equation for the line. Let's do it like this. Ask yourself now, what's the gradient, what's the y-intercept? And hopefully you realize that the gradient in this case is 7 and the y-intercept is 8. Weird that we use M and C, isn't it, for M for gradient and C for y-intercept, but there we go. A couple of more awkward examples of this, right, is if I put a number before the y, something like this. Okay, because we wouldn't want, apologies, I've got that. There we go, that's hopefully better. Let's go back to my drawing. We wouldn't want 3y equals. It's almost like changing the subject of the formula. We'd want y equals. So instead of that 3 times in that y, we need to divide this side by 3, but we are going to divide both things by 3. Okay, so the gradient is 5 divided by 3. And because 5 doesn't divide by 3, I'll leave it as a fraction. Whereas the y-intercept is, and people will forget the minus here, so check your answers that you've right, that if there's a minus in the middle, the y-intercept is negative, so it's -9 over 3. 9 does divide by 3, is 3, but again, not forgetting the minus, it's -3. Final example of this is, I don't know, y minus 2x plus 7 equals 0. Well, in this case, it doesn't look like this. Again, we've got to change the subject of the formula. We need y equals, so this needs to go over the other side, as does this. So we get y equals, don't worry about the 0, that just means there's nothing there at the moment, but things are about to come over. The minus 2x is positive, and the plus 7 is negative. Therefore, the gradient is 2, and the y-intercept is -7. Let's move on to parallel and perpendicular lines. If lines are parallel, they have the same gradient, the same steepness, but a different y-intercept. So in these two lines, both the gradients are 2, but on the top line, the y-intercept there is 4, and in the bottom line, because of the number there, the y-intercept here is -3. Slightly more difficult, an awareness of perpendicular lines. Again, they will have different y-intercepts. This one, as we can see, is +4. This one, as we can see here, is -1. However, they don't have the same gradients, okay? What you've got to do to get, if you're given the gradient of 1 and you want the gradient of the other, you need to flip sign and reciprocal. Wow. Difficult, right? So, for example, if the gradient of one of these was 2, right, then the other line, the perpendicular line, we'd flip the sign. So instead of positive, it would have a negative gradient, and we would take the reciprocal, which is a flip. So if you flip a whole number like 2, though, it becomes 1 over, so it would be 1 over 2, right? Another example, if one had a gradient of -3 over 5, then the other perpendicular line would have a gradient of plus, flip the sign, and flip reciprocal of the fraction. So instead of 3 over 5, it's 5 over 3. And in our example, we can see if one is a half, the other one, flip the sign so it becomes minus, and instead of 1 over 2, it becomes 2 over 1, which is just 2, so -2. Okay, using those ideas, you're going to go through these questions. One other thing I want to point out to you, because this talks about gradients and crossing the y-axis, etc., is something like this. Does a point belong on a line? If it does, you can swap the x and y coordinate of the point into the line equation, okay, and it'll still work. So this tells me that y is equal to 3x minus 2, right? Is 3 times 3 take away 2 equal to minus 2? No. Is 3 times 0 take away 2 equal to 2? No. And no, and keep trying. However, when we get to the end, is 3 times this x going to 3? Is 3 times 3, 9, take away 2 equal to 7? Yes, it is. So that point belongs on that line. Try some others. Let me know if you're having a problem with those. Okay, we're back here. Now, linear inequalities is our next thing. It's like solving equations, this, right? I don't know if you'll get one of these, right? What I do know is you'll get a question from the next topic, which is locating regions given by linear inequalities. I think both? Maybe, maybe not. This one's certain, this regions one, drawing graphs. This one, maybe, maybe not, but we need to do a couple of examples just in case. So basically, this is solving equations, but instead of an equals, we've got an inequality like less than or greater than, okay? Same rules apply though. So if we were solving this, it doesn't matter if the letters n or x. In fact, I'll leave this one for you to do. Just think about moving the minus 3, treating this like a magic bridge, right? But it stays as an inequality, okay? And then moving the 7, which is times in that x, blah, 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 okay? I'll do this one from the sample paper from a few years ago, okay? Here, the reason I'm doing this one is because I don't like this 5n being here. I wanted to come over with the other ends, the subject terms in this case, okay? So 7n minus 5n, because it's positive that side coming over here, is less than, and I've still got 11 there. So 7n take away 5n is 2n, and it's less than 11. And the final step then is to divide by the 2, I guess, so 11 over 2. And do not change that to a decimal, leave it like that, okay? There's just no need. If 11 divided by 2, great, we can give a number answer, but where it doesn't, you can leave it. So what we know now is n is less than 11 over 2, but in your mind, you guys know that 11 over 2 is 5.5, okay? It's 5 point something, right? That's good enough here. So if n is less than 5 and a bit, 5 and something, right? What is the largest integer whole number value for n that satisfies the inequality? So n could be 0 because that's less than 5.5. It could be 1, that's less than 5.5. It could be 2, it could be 3, it could be 4, it could be 5. It can't be 6 because 6 isn't less than 11 over 2. So what is the biggest number it could be? Is 5, okay? Again, you're going to try that one, but I'll just do this one for you quickly. Here we have to form the inequality, then solve it, and then find the greatest or smallest, whatever it asks us for in part B, okay? Arthur, Sean, and Kezia all have some £1 coins. Arthur receives n pounds. Right. Sean is given 5 times as much money as Arthur. So if Arthur has n and Sean is given 5 times as much, then Sean has 5n, 5 lots of what Arthur had, okay? Kezia receives 3 times as much money as Arthur, okay? So Kezia receives 3 times what Arthur got, so she only gets 3n, right? Plus an extra 7, add on an extra 7, okay? We're then told what the inequality is. Sean was given less money than Kezia. Sean, who got 5n, was given less money, less than Kezia. Okay, write down an inequality in terms of n that illustrates the fact that Sean received less money than Kezia. Job done. Now, I'm not sure where you're meant to solve this because the next it jumps straight to what was the greatest amount of money that Arthur could have been given. In other words, what's the greatest value of n? Because that's what Arthur was given was n. However, I think we'll just solve it up here. So exactly like we did above, the plus 3n coming over here. So 5n take away 3n is 2n. Divide by the 2. So this time, it's set n is less than 7 over 2, which is 3.5. So what's the biggest number that n could be? Well, it could be 1, it could be 2, it could be 3. It can't be 4 because 4 isn't less than 7 over 2. So the biggest it can be is 3. Okay. These are difficult. We're going to have to do these in class, okay? And it's going to be very, very difficult for me to draw them. We need to be able to draw these 3 lines on here, on this graph paper, okay? And then I'll explain to you about the shading bit or the draw the region. I'll explain what that means. First of all, the main marks, how to draw them. I want you to think of the inequality in here a little bit like when we're solving them. Think of it as a magic bridge. Think of it as an equals. That is what is going to allow us to draw these lines, okay? The first line we're going to draw is x plus y equals 6. If I was drawing this, I would get a little table of values, x and y, okay? Have a look at the x-axis, 0, and it goes up and down in 2s from there. So we've got, I would only look at the positive values here. So the first couple are 2, 4, and 6. So I'm going to use 0, 2, 4, and you could do an extra one. It depends. 3 is enough points. If you want an extra point, you can, but we'll stick with those for a second. So in order for x plus y to equal 6, if x was 0, what would y need to be? 0 plus what makes 6? 6. 2 plus what makes 6? 4. 4 plus what makes 6? 2. Now, those 3 points, and I'm going to have to zoom in and hope that you can still see, okay, those 3 points need to be plotted on here. So my first point is when x is 0, y is 6, which is there. Okay, when x is 2, y is 4, which is about there. And when x is 4, y is 2, which is there. All right, and we can join those up. Oh dear me, here we go. Good luck. Insert. All right, how are we going to do? No, I can't. It doesn't matter. I'm just going to talk you through the list bit, okay? So what we're going to do is connect those. Got my pen back. Connect those 3 points up with a straight line and continue that line. Continue it in that direction and continue it in that direction. Look, I could have a go. I'm nervous about having a go, but I could have a go. Even further than that, keep it going to the edge of the graph, okay? And all the way up there. Right. The next line I want to draw. Oh, it seems to have gone into. It's going well, isn't it? Okay. Let's get my pen back. Okay. The next line I want to draw is y equals x over 2 plus 3. Again, the values of x that I think would be good to use are 0, 2, and 4. And we'll go what y is, okay? This time it's a y equals 1 rather than an x plus y like it was there. So y equals, so if I put 0 in there, y equals 0 divided by 2, which is 0, plus 3, which is 3. 2 divided by 2, 4 divided by 2, which is 2, plus 3 is 5. So this time, when x is 0, y is 3, which is there. When x is 2, y is 4, which is the same point as that one. And when x is 4, y is 5, which is about there. And apologies if I'm slightly out, okay? And again, straight line, ruler, not like I'm doing, all the way through those 3 points and continue at either side. Final line, x equals minus 2. Don't need a graph. I don't need a little table for this. X is always minus 2, which is here. All right? X equals minus 2. So it's a straight line up through there. Now, quickly to explain. Those 3 lines will effectively make a triangle. If it was 4 lines, it would make a 4-sided shape. You can see the triangle that's being made by those 3 lines. It's there, okay? You can get away with just colouring that in. That is the region that satisfies the 3. Just to prove to you it is, though, okay? We drew x plus y equals 6, but actually the inequality was it's less than or equal to 6. In other words, I'm looking for the region below that line, which is this side. This was this line here, okay? But y is greater than or equal to this, so I'm looking for the region above that line. And the final one, x is greater than minus 2. So I'm looking for anything for x is bigger than minus 2, which is this side of that line, above that line, as it were, in the x direction. So if I want to stay below that line, above that line, and to the right of that line, The only region in there that does that is that triangle. But like I said, you can get away with just colouring in the triangle that is made. And that's the end of that. Little section is transformations of graphs or functions of graphs, same thing, okay? They will often draw a graph and not tell you what it is and just say, oh, we're going to call this f of x or g of x, which is what you see in this here, okay? So let me get my pen again. So, for example, f of x, or it might even use g of x or something like that. But that basically is a graph that we're not going to tell you what it is because it's not important what the graph is, right? It could be the sine graph, it could be the cos graph, it could be a random straight line graph, it could be a curved graph, it could, anything, right? But they will draw it and call it whatever, okay? It's what we do to this that tells us where we're moving, where we're transforming the graph, or how we are transforming the graph, okay? If we put a number at the end and it's being added on at the end, it shifts the graph up, okay? Which means it is changing in the y direction. It is going up the y-axis. Or minus a number at the end, whatever that number is, d they call it here, but just any number, we're going to shift the graph down in the y direction. So only your y coordinates would change because they're moving up and down. It's not moving left or right. If we put a number inside the bracket, weird, it doesn't become an up or down move, it becomes a left or right move, and this is just something you've got to commit to memory. Again, it's another one of those things, okay? If it's negative inside the bracket, like -2 or -3, okay, you would expect that to be left because that's where the negatives are, to the left. But the opposite happens, right? A negative in shifts to the right. So it's a change in the x direction, but it's to the right. And the flip of that is you'd expect plus a number in the bracket to move you right, but it actually moves you left. So again, it's in the x direction, but it's left. Okay? Again, a minus before the f of x is a reflection rather than a movement up, down, left, or right. Okay? If it's before the f of x, you're reflecting in the x-axis. So if it was something like this, and you reflect it in the x-axis, then that is the mirror line, the x-axis. So it starts here, comes down, meets there, and goes above. Ooh, yeah, it looks quite fishy. Okay, if it was in the, this is a bit more awkward to draw actually, isn't it? Okay, if it's a reflection in the y-axis, it's this line, okay? So what was to the left is now to the right, and this bit, which was to the right, is now to the left, right? So there's a flip in the using the y-axis as a mirror line. This is using the x-axis as a mirror line. Hopefully they are a little bit more difficult to draw. Now, if you are given any coordinates of the graph, when you do your transformed graph, you need to say what they have now become. If there aren't coordinates, it's a sketch and it doesn't matter. As long as you do the right sort of thing, you're fine. If there are coordinates, we've got to give them. And I'm going to take this as an example. Okay. We are asked to draw this. The -3 is in the bracket, not out. So it's a left or right movement. And although the minus would suggest left, this is right 3. Because I've been given these 3 coordinates, all right, I'm still sketching, but I have to give the values. I can't just go, I'll just move it to the right 3. Okay? So what was -1 is going to move 3 over 0, 1, 2. However, it's not moving up or down, so it's going to move to there. What was 5 is going to move 3 over 1, 2, 3, and it's only a sketch, like I said, is now 8. But again, okay, the y isn't changing here. It's just an x direction move, so it's moved 3 to the right. So it's only affecting the x coordinate, okay? And same up here. It's not going to move up or down, so it's still going to be 7 up. But from 2, it's going to go 1, 2, 3, 4, 5. It's almost directly above this, isn't it? Okay, and it's now 5, 7. So it's moved 3 over, and then we connect it up. Better than this is so difficult without on the screen. All right, and you'd get away with that. So everything has moved, every coordinate has moved 3 to the right, but the y coordinate is not affected. Okay, all right, I should have done that on here. You must include the coordinate of the points of intersection of the graph with the x-axis, which I've done. Okay, which is there and there. And you must include the coordinates of the highest or lowest points. And there, that's the highest point. So we've done that as well. So we've given all the coordinates we need. I just should have drawn it on that rather than up above. Okay, let's just talk through a few more now. This curve has transformed to this. Take a little look at it. As it moved up, down, left, right, or reflected? Well, it's clearly moved up. Okay, how far up? Well, take a point. Right, always the best. Take a point. That was at 0 there. Where is that point on there? It's now there. So what this is a movement of 2 up. Okay. What about this one? Let's have a look at this. Ooh, this looks like a reflected one. Okay. I'm going to draw them on here though, just so you can see. If I was reflecting in the x-axis, what was above would come below, and what was below would come above. Right, if that was the x-axis. If it was the y-axis, what was to the right, okay, would come to the left. So this kind of thing here would be over here, and that, what was on the left, would go to the right. Let's take a look. And it's the second one. It's a reflection in the y-axis, not the x. So if we go up, a y-axis reflection is with a minus in the brackets, okay? So I'll just write that there, and we'll finish, and I'll let you try some of the others. So y equals f of minus x. And we're done with that one. On to averages. The next topic. My voice has gone a little bit because I'm recording this a different day, this video. So my apologies if it sounds a bit hoarse in this video, but that's is what it is. We'll keep going. So averages. I've started writing something there. I'll come back to what that means in a minute. Let's just go through what they are. Mean is when you add up all the numbers, get an answer. So I'll put equals and then divide by how many numbers there are. So the mean of in part A, you would add these all up. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers here. You'd add up the 9 numbers, press equals, and divide by 9. This is non-calculator. I can't see them making you add up that many big numbers. Not that because you can't do it, because it'll just take so long. So I've probably taken this from a calculator paper. Although no paper one. Anyway, try it without a calculator. Try and add them all up as best you can and divide by 9. Should get a nice answer. The median is the number in the middle when they are put in order. Just finding the number in the middle without putting the numbers in order of size is meaningless, right? But if they're in ascending order, smallest to biggest, or descending, it doesn't matter. In order, finding that middle number, that's the median. If there are 2 numbers in the middle, okay, for example, 3, when there are 4 numbers, the middle is between 2 numbers. So the median would be the average of the 2 numbers either side. So if 6 was to the left and 8 to the right, then actually the median isn't even in the list because the median is 7 because that's what lies between 6 and 8, okay? The mode is the most common number, the number that appears most often in the list, and the range is the biggest number, take away the smallest. One thing to pick up on the mean, and I did draw this here, okay? If I told you that 5 numbers, these 5 boxes have a mean, I don't know what that's disappeared, have a mean of 7, okay? That 7 doesn't get placed in those 5 numbers. It doesn't mean that the 7 is one of those numbers. It means that they average out to be 7. So what that will tell you that the 5 numbers, if I times that by the mean, 35, it means that they add up to 35. If I know 4 of them, then I can work at the 5th by making it add up to 35, for example. Okay, I haven't got a lot to say about these questions. Just do them, work at the mean, work at the mode, etc., etc. These questions here are worth mentioning. Okay, let's take this one. All right, you might get stuck on some of the others. Just let me know. Come and see me. Which one of the ones you can't do. So we've got, there's 4 numbers and they're all going to be odd. They're all positive odd numbers. The mode is 7. So all that means for a minute is I'm going to put at least 1 7 in the list. Don't know where for a minute. The median is 6. So 6 because there are 4 numbers, 6 can't go in a box because it's in the middle, which is between these two. However, what that does mean is I can't put 7 here or here because 7 is bigger than 6. So the 7s that I was had here are going above the median. So if the median is 6, but the number to the right of it is 7, the number to the left of it must be 5, which kind of gives you that median of 6. Does it tell us about the 4th and final number? No, it just says which odd numbers could Cadvan have written down. Well, we've got 3 of them. The other one, we can just pick another one. Right? There's no other rule to help us work it out. It doesn't say but the mean or anything else, or the range or whatever. So for this to be an odd number, it could be 1, it could be 3. It can't be 5, because otherwise 5 would also be the mode, and it can't be 7, because they're in order of size. Right? So I'm going to go with 3, but you could have put 1 there. What else have we got? Okay, find 4 different positive whole numbers. 4 numbers again. 1, 2, 3, 4, where their mean is 8. Now, if there are 4 numbers with a mean of 8, that means that they need to add up to 32. The range is 8. That means the biggest take away the smallest is 8. And the median is 8. Let's start with that, okay? For the median to be 8, right there. Now, I could put 7 and 9 either side, but I am told... No, I'm not told. I thought that they had to be even. Did they say 5 4 different? No, it doesn't say that. So that's exactly what I'm going to do. Sorry if you can hear the printer going off behind me. I'll speak louder. So 7, 9. Okay. They are going to add up to 32. So far they added to 16. However, we also need a range of 8. So this take away this has to be 8. So this needs a bit of trial and error. Okay. 9 and 7 is 16. Okay, let me write that there. 7 and 9 is 16. But we need them to add up to 32, so I need another 16 here and here, all right? But with a difference of 8. So a little bit of thinking probably will tell you that those 2 numbers are 12 and 4. And the 12 and the 4 give you a range of 8, but add up to 16, which when added to the 7 and the 9 mean the whole thing adds up to 72. And finally, congruence, a higher level thing. I've done some scribbles on here already. I'll just talk about what those scribbles are, okay? So what I want to say about this is congruent means identical, okay? Proving the 2 triangles are identical. Now, there are 4 ways we can prove 2 triangles are identical. One of those ways, let's start with this box here, 3 sides are respectively equal. What that means is we have 3 sides equal in the same order on the shape. So 1, 2, 3, 1, 2, 3, and they're all the same size. So that one is the same size as that one. The one next to it is the same size as the one next to it here. And then the third is also equal to the third one over here. Okay, so we can look out for that as we go through here. The second condition of congruency is side angle side, right? That doesn't mean any 2 sides in an angle. The angle has to be included, which means between the 2 sides. So if I have 2 equal sides there and there, and I can find another triangle with 2 equal sides, this one and this one. What I mean by equal, I mean that this is equal to this, and the second side is equal to the second one, not the sides on the same triangle are equal. Okay, let me just point that out there. And the angle has to be included, which means between those 2 sides. Where those 2 sides meet, that's where the angle is, okay? So 2 sides of the included angle are respectively equal. The second one is angle side angle. The angle there is the same as this one here. The angle here is the same as this one here, and the side included between the angles is equal. And the third one is just for right angle triangles. That they have a right angle, fantastic. That the hypotenuses are equal, okay, and then one other side is equal. Now, what I've said at the top here is 3 angles being the same is not enough to prove that they're congruent, okay? So if this triangle and this triangle here are the 3 angles on this one were the same as this one, it doesn't mean that they are identical. What they are, though, is similar. They could be identical, but they're definitely similar. One could be a scale factor of the other, so twice as big or 3 times as big, etc., etc. Miss Terry has joined me in the room and would probably tell me I'm going to get this one wrong, right? So help me out on this, Miss Terry. They won't mind me doing this. So G is the midpoint of FH. So I've shown them that F to G and G to H are equal, and EG and FH are perpendicular, meaning that they meet, EG and FH meet at right angles. Prove that EFG and EHG are congruent triangles. Now, my gut feeling here is that because these are perpendicular and then these two sides are the same length, in other words, that's the midpoint. If I go along here and up here, that by nature means that that is equal to that in size.
That's right.
Yeah. Therefore, the condition here is both my triangles here, EFG and EHG, have a right angle in them, which is here and here. The hypotenuses of these triangles are the same, here and here. And then we have another side that we know is the same, which is GH is the same as FG. So that's the condition of congruence. But you need to go on and explain that, exactly what I've said there. Both the triangles have a right angle. The hypotenuses, which are EF and EH, are equal. And then the sides FG and GH are also equal. So the condition of congruency is RHS. And we'll do one more, and then you can try the rest of these. I'm going to find something that's a bit more difficult than this. Ooh, that looks nasty. Let's do this. I'm glad Miss Terry's here. Right, triangle ABC is an isosceles triangle with ABC. That's angle ABC. So ABC, which is this angle here, okay, is equal to ACB. Now, what that means is that this is, yeah, it does it. It says it's an isosceles triangle. So also we know that the length from A to B is the same as the length from A to C. So I'm just going to draw that triangle out here. Don't know if it'll help me. That they are the same length and they are the same angle. That's what we know so far. P and Q are points on A, B, and AC respectively, such that AP, A to P, which is this bit here, just that little bit there, is equal to AQ. Prove the triangle ABQ, which I am going to try and draw this, which is that ABQ is congruent to triangle ACP, which is the same one going, my apologies, oh dear me, AP and C is done that. Prove that they are congruent. Well, what we know so far is that that side there, which is AQ, is the same length as AP. We also know from the isosceles triangle that A to B is the same length as A to C. Miss Terry's nodding along, so this is good. And because they share this angle A, they share it, we know that that angle there is the same as that angle there, okay? And that is a condition of congruency. We've got this side being equal to this side being equal to this side, and the included angle. So the it's side angle SAS, yeah? And you need to go on and explain that a little bit better, exactly what I say. So you need to say, okay, because AB is equal to AC because of the isosceles triangle. AQ is equal to AP because we're told it. Here. And then finally, angle A is on both triangles. Angle A on both triangles. Therefore, condition of congruency, SAS. And we'll stop there. Try some of the other ones in here and come back to me if you're struggling.